Okay, so this now would be a video briefly discussing about lipids, classes of lipids, and their general characteristics. But before we delve into all of that, let's first try to define what lipids are. Well, when we're going to talk about structures, lipids among the four biomolecules are the most diverse, meaning that unlike proteins, which are composed of amino acids, nucleic acids, which are composed of nucleotides, and carbohydrates, when they are polysaccharides, they are made up of monosaccharide units. Lipids are actually not really composed of monomers. In fact, they have several general structural formulas, but there should be one thing that is very common to all of them, and they are all insoluble in water, or they are hydrophobic. Alright, and in this case, you could also term that they are non-polar, because water is polar and lipids are non-polar. That's something that we should have known ever since beginning of time, or probably since we have discussed general chemistry. And now we're going first to discuss the types of lipids based on structure. Then we're going to discuss about characteristics, then finally to some kinds of reactions. Alright, as much as I want also to discuss about biosynthesis of lipids, because it's a very interesting topic, again, that's not anymore the scope of general biochemistry, at least at the level that we are in at the moment. Alright, so we're going to discuss the types of lipids based on structure. So the first thing we have to know is this one. We know that RCOOH is the structural formula, general formula of carboxylic acids. But in the case wherein the R here has 5 or more, actually some references say 3 or more carbons plus 1, so that would be 5 plus 1 equals 6, or 3 plus 1 equals 4, or anything longer than that, you would call this carboxylic acid as a fatty acid. And that's why it's called an acid, because it has the carboxylic acid's functional group here. Of course, we know that as the carboxyl group. Now you may be asking, how come the fatty acid structure here is non-polar? We're talking about lipids when you have a polar group here. Well, the thing is, if you have something like a COOH, then you combine it with a very long carbon tail. We know that this tail is non-polar as opposed to this polar portion. So if you're going to match this small polar portion to this very long non-polar portion, of course, the non-polarity of this would win over the polarity of the terminal carboxyl group. That's why at the end it's still non-polar. Now, fatty acids, as we would discuss more specifically later on, most of the fatty acids commonly found in nature are unbranched. Alright, they are straight chain, and they could exist either as saturated or unsaturated. Now, when we have fatty acids, we could actually have fatty acids combining to several backbones. Alright, backbones. And actually we have 2 backbones here as demonstrated. The first backbone is this one. So the name of this, if you can recall this, or if you've encountered this is a 3-carbon alcohol with 3 hydroxyl groups. The name of this one is glycerol, or trivial name glycerin. Alright, and the other backbone is this one. This is a longer one. This is an 18-carbon backbone with an amino group right here and a double bond at carbon number 4, between 4 and 5. The name of this one is sphingosine, sphingosine, whatever. Alright, so these are the 2 backbones. Now if you have glycerol right here, you can see that we have 3 hydroxyl groups. Alright, and this one is a carboxylic acid. And if we could recall in organic chemistry, if you make an alcohol and a carboxylic acid react, that process is known actually as esterification, right? That's a carboxylic acid plus an alcohol. But the thing here is you actually have 3 hydroxyl groups, meaning that one glycerol molecule can esterify with 3 fatty acids. So you could have here 1, 2, 3 fatty acids esterified to a single glycerol backbone. Okay, and to give the name of this one, I'll first introduce again as a review in organic chemistry that this one, the RC double bond O, alright, in this general formula, this one is known as the acyl, right, as the acyl group. That's why when you combine the fatty acids in glycerol, you would call them, we have 3 acyls here, that's why you call them triacyl glycerol, or TAG, or the more trivial name of this one is triglycerides. So this is the general formula of triglycerides, if you've ever encountered that word. Now, if we have glycerol, then we have this one. If you could see this is PO4, right? This is actually a phosphate group. Then it also has a head group X, alright? This one actually distinguishes the different types of this general structure. So we have here, instead of 3 fatty acids, we have just 2, because the third one, the third oxygen, or the third hydroxyl in glycerol is bonded to the phosphate group with an additional head group. Instead of calling this a triglyceride, well, this is a diacyl glyceride without the third, but if it has a phosphate here, the name of this now is a phospholipid. Generally, this is the general formula for phospholipids. Alright, so the difference between a phospholipid and a triacyl glycerol is that one of the hydroxyls, instead of having a fatty acid, has a phosphate group with a corresponding X head group. Now, if the backbone is not glycerol, but instead it is sphingosine, the thing here is it's the same with glycerol in that it could esterify. No, actually it could bond with 3 fatty acids. It could esterify 2 times, 1 OH here, 1 OH here. Then an amino group could also join, forming an amide bond. So at the end, we will still have 3 fatty acids combined to the sphingosine, 1, 2, 3. So same capacity as with glycerol, but of course an entirely different structure because of an entirely different backbone. Now the lipids of this class are known as sphingolipids. So what are the importance of this? Well, for example, triacyl glycerols are very much known as a source of energy. Alright, when for example we lose our carbohydrate reserves, we run out of sugar, the next thing that our body will tap are lipids, because to mention again, when we talk about the amount of energy provided for, lipids would provide 9 kilocalories. Alright, 9 kilocalories as opposed to carbohydrates and what's the other one? Proteins, which only provide 4 kilocalories. Alright, but then again, carbohydrates are preferred because they are the ones that are used by our brain. Okay, so phospholipids in turn are very much known because they provide the structure of the cell membrane. Remember, we mentioned the cell membrane as a phospholipid bilayer, and so this is actually the one that comprises much of our double membrane. And sphingolipids, one of the I'll just give out I'll nitpick a particular sphingolipid. The name of that sphingolipid is sphingomyelin. Sphingomyelin is the major lipid found in, well, what's myelin? Myelin sheets found in our nerve cells. Alright, so very diverse functions. Now this one, we know that this is the type formula of an ester, RCOOR prime, and if the ester we have here is a combination of a very long chain alcohol, such as this one, and let's say that this is something like 10 carbons or more, as long as it is a long chain, and the fatty acid, alright, as opposed to glycerols, or so as opposed to glycerol and sphingosine, the alcohol that we have here is only monohydric, only one hydroxyl group, as opposed to this one, which is trihydric. Alright, we would now form a lipid, specifically an ester, which is known as a wax. And if you draw it, alright, we say that fatty acids are long chain and they are flat, they are straight chain. It would look something like this. Then the alcohol is long chained also, so it will even be longer. Imagine how flat this would be. If you lay it out, it would be long and flat, and you stack them together. That's a lot of van der Waals, and we know that van der Waals forces are non-polar. They give the substance non-polarity. That's why waxes are very insoluble in water. That's why we even use them as water repellents, right? We use wax, for example, in fruits like the ones we coat for apples, in order for them to be waterproof, and also the wax could also serve as an insect repellent. Alright. Now this one right here is the structure of one of the essential fatty acids we need. That's why it's called essential. Arachidonic acid. Arachidonic acid is actually a precursor for many of our endogenous lipid-derived molecules known as eicosanoids. Eicosa means 20, alright? Eicosa means 20. Even if we count this, it would be 20 because eicosanoids come from arachidonic acid. This one should also be 20 carbons: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And there are different eicosanoids, and they have very important functions. If you're taking up health sciences, you should know them very well. Examples of these ones are prostaglandins. Alright. Prostaglandins are eicosanoids that are responsible for response to pain, and that's why, for example, drugs such as aspirin or the cyclooxygenase inhibitors target prostaglandin synthesis. They inhibit the synthesis of this because if you inhibit prostaglandin synthesis, you will not feel the sensation of pain. Another class of eicosanoids are leukotrienes. This is very much encountered in the case of asthma because leukotrienes in general permit vasoconstriction, and when you have vasoconstriction, you are more predisposed to coughing, wheezing, or asthma or COPD. So if you inhibit synthesis of leukotrienes or prevent the receptors that leukotrienes target, you would prevent vasoconstriction, so you would prevent the patient from having acute asthmatic attacks. And thromboxanes are another class of eicosanoids. Thrombo, meaning something related to platelets. Thromboxanes are actually participative in platelet activation, wherein once platelets are activated, it will now result to ultimately the formation of a platelet plug. So this has to do with blood clotting. If you lack thromboxanes, there will be problem in clotting, okay, with a particular patient lacking thromboxanes. Finally, the last class of lipids I'm going to demonstrate here have this nucleus, and actually these lipids are known as steroids. Steroids, alright? So they have this nucleus here, a 4-ringed nucleus. The name of this is cyclopentano perhydro. Yes, it's a very long name. Phenanthrene. So to cut the name down, because it looks very long, phenanthrene here is actually the portion here. Phenanthrene refers to these three six-membered rings here. Cyclopentano, of course, referring to the cyclopentane here. Perhydro means that all the possible double bonds here, or the unsaturations here, have been fully occupied or saturated by hydrogens, because phenanthrene is aromatic. It has double bonds here originally. You remove or you obliterate all of those bonds and fill them up with hydrogen. So that's why we come up with this name, or it's also abbreviated as CPPP. Alright, cyclopentanoperhydrophenanthrene. Now, steroids are very essential. They make up what we call as the adrenal hormones. There are several. For example, glucocorticoids. These have very diverse effects on the body. This could lead to buildup of muscle, production of red blood cells, rearrangement of fat. It could actually go somewhere. That's an adverse effect. It could also promote diabetes and ulcer. But a very important pharmacologic use of glucocorticoids is that they are anti-inflammatory. They prevent white blood cells from going to the site of infection, because if they do, the certain site of injury will swell. So if you prevent that from happening, the site will not swell. That's why it got its anti-inflammatory effect. Another class of adrenal hormones are mineralocorticoids. They regulate the balance of minerals. Here we are referring to sodium and potassium. Alright? And they also regulate fluid balance. That's why if there's a problem with mineralocorticoids, you could have problems with your potassium and sodium levels, as well as have a propensity to develop edema, or development of fluid at the sites where fluid is not supposed to accumulate. Then finally, sex hormones.